practical electricity, all right, the first set, we actually get them from the previous chapter, all right? In the previous chapter, in current electricity, or even static electricity, we learned that, okay, current is the rate of flow of charge, right? Okay, we also learned that potential difference is the work done to drive 1 unit charge around through the component, right? Through the component. Okay, so when we combine these two formulas together, right, if I want to know what is the work done, okay, or the energy converted into thermal energy, or we call it internal store, right, transfer to the internal store, we can rearrange this formula, W equal to VQ, right, and Q is equal to I times T, right, so you get V times IT, all right, V times IT. So this is actually the formula that we need to know for this chapter. You can write it as energy, or you can write it as work done. This is when AI is getting too smart for its own good. Okay, try to correct me. Okay, so energy is energy. Okay, in this case, I can say energy because the work done can be transferred to internal store, right? So I can write energy equal VIT or work done equal VIT. In fact, for some of the classes, I tell them it's the vitamin E formula, okay, vitamin E formula, because E equal VIT, all right? So this is the first set of the formula, okay? The second set is, let's say, if you are given the voltage of the appliance. Now, for this chapter, right, practical electricity, we are dealing with appliances in the home, right? So we talk about voltage. We don't talk about potential or EMF anymore, right? We say, okay, this kettle has a certain voltage, uses a certain voltage. This iron uses a certain voltage and certain power. So how many watts, how many volts, right? So we don't talk about PD, but it's still the same V lah. It's basically volt in volts. Okay, so voltage, let's say we are given voltage and, or rather, let's say we are not given voltage, all right? We are given only current and resistance. Then how do we use this formula? Of course, we can use V equal I times R to find V and then plug in this formula. But it's more convenient if we know the formula that we can sub in straight away, all right? So let's get rid of V, right? So I put V equal IR, I sub into this formula, I get E equal to what's that? IR, V is IR, right? Times IT. Okay? So it's I squared RT. Okay, so this is the second formula. I call this 1A, I call this 1B. Okay, so E equal to I squared RT, sorry about my handwriting. E equal to I squared RT is the second formula. And the third formula is if we have V and R but don't have I. All right? If we have V and R and don't have I. So I can, starting off with E equal VIT again. From E equal to VIT, the vitamin E formula, I get rid of I. Okay? I get rid of I equal to V over R. I get rid of I. Okay? I get E equal to V times V over R T, right? So you get V squared over R T. Okay? So this is the third formula. All right, I call it 1C. Okay, so basically we have three forms of the formula depending on what you are given. If you are given V and I, you write E equal VIT, you use E equal VIT. If you are given I and R, you use E equal to I squared RT. If you are given V and R, you use E equal to V squared over RT. Okay? Now, some of you may ask, do I need to memorize so many formulas? Actually, don't need. You can just remember E equal VIT And whenever you're given something else other than V and I, you can use V equal IR and convert and then find V and I and use back 1A. But from experience, it's always better to memorize all three and plug the correct formula in straight away. All right? So anyway, after a while, when we talk about it, you will get used to it and you will remember it. Okay? Now, this is the energy, this is a set of energy formula. All right? 1A, 1B, 1C, these three are energy formulas. We also need the power formulas. So, like for example, when you're given an iron, all right, the power rating is so much. Then I ask you to find its current, the current that it uses, the resistance, and so on. All right, how much energy does it use in 1 minute? You must be able to calculate. So, we use this very familiar formula, all right, E equal to energy equal power times time. All right, energy equal power times time. And I replace energy with power. Okay, so how to do that? Energy equal to power times time. Okay, or power is equal to energy, work done per unit time. Right? We learned this in Sec 3. Power is work done per unit time. So if I take E equal VIT, right? Okay, and then I divide by T, what do I get? I bring the T from the right side, E equal VIT. I bring the T over to the left side, become energy over time equal VI, right? Are you following? Energy over time is actually the power, right? So power is equal to VI. Okay? 2B. So y'all get the idea. You can get another set of formulas for power just by bringing the T over. Alright? So for E equal to I squared RT, also same thing. Right? So I bring the T over, E over T. Okay, I can do it straight away. Skip one step. Okay, so E equal to I squared RT. So E over T equal to I squared R, so power equal to I squared R. Okay, so this is the second formula. Right, and the third formula you can guess, it will be P equal to V squared over R. Okay, so same thing. I bring the T over, I get V squared over R. So power equal to V squared over R. So this is the third formula for that you get from the first set. Okay, so the two sets of formulas are actually very closely related, right? E equal VIT, power equal VI. E equal to I squared RT, power equal to I squared R. Energy equal to V squared over RT, power equal to V squared over R. Basically, the second set is just without the T, without the time. Okay, because energy over time is power. All right? So we can, if you memorize one set, the other set is easy. Okay? So it depends on how you want to memorize it. You want to memorize the power, then you just add a T behind to get the energy. Or you want to memorize the energy set, and then you just remove the T to get the power. Okay, so this set of formulas, you need to remember how to use. Okay, the fuse is, actually I have the fuse here. I have a fuse here. It's made up of two metal caps, right? Okay, let me draw it first. It's made up of two metal caps. And fuse wire in between. Okay? And from the outside, what you will see is just a cylinder with a metal casing. All right, and there will be a fuse rating written there. Okay, so let's say 5 amperes. That means that this fuse wire inside will melt when it exceeds 5 amperes. Fuse, right? What it does is that it will melt or blow when the current is too high. All right? The fuse will melt or blow when the current exceeds the rated value. The rated value, okay, will be written usually on the fuse itself. Okay? After the fuse blows, it will disconnect the appliance from high voltage. Okay? All right, so the key thing that you need to know is the fuse will melt when the current exceeds the rated value. Okay, so this is the key thing you need to know. Now the next statement here, what does this mean? Disconnecting from high voltage. Okay, are we talking about current or are we talking about voltage here? A bit confusing, right? Are we talking about current or voltage? The fuse will blow when the current is too high, right? Okay, it will protect the user as well as the appliance. Because if the current is too large, the appliance will also be damaged. But the next thing that happens is even more important. When the fuse blow, okay, let's say this is the live pin, and this is the appliance. Let's say we have a heater, all right? This is the neutral wire, neutral pin, and live wire is at high voltage, 240 volts. Okay, neutral wire is at 0 volts. When you place the fuse in the live wire, when the fuse blows, okay, I deliberately draw the disconnection there. When the fuse blows, the appliance will be at 0 volts. Okay, this is important, all right? Okay, so this is actually, the third statement is actually talking about this. And I'm going to relate it to the next question. I'm going to come back here again. But the next question is asking you, why is a fuse or switch connected to the live wire and not the neutral wire? Okay? Why is a fuse connected to the live wire and not the neutral wire? What will happen if we connect the fuse to the neutral wire instead of the live wire? Okay, let's draw it and see. Sorry? Doesn't even what? Doesn't do anything. What do you mean by doesn't do anything?
Because the main point of it is to stop the current from being too high.
Okay, but you say it is to stop the current. Is that correct way to phrase it? The fuse, all right, the fuse, when we draw the fuse, we always draw a rectangle with a line across. Compared to the fixed resistor, we don't have a line across. Fuse is exactly the same except it has a line across. The line across stands for the fuse wire. The fuse wire is designed to melt at exactly that stated value there. Okay, but just now Aaron was explaining in terms of current, right? So he said that when the fuse blows, right, it stops the current from flowing, right? Okay, but if that's the case, why do I need to put it in the live wire? I can put it in the neutral wire. Is it about voltage or is it about current? Just now Aaron said current. So what is Aaron saying? Aaron is saying that if the current is very high, the fuse blow, right? Then the current will be stopped after the fuse. Is that what you're saying, Aaron? Right? There is a misconception, because I'm purposely asking this question because I want to draw out the misconception. Remember when we started talking about current, when I introduced current to you, right? Remember I told you that current is the same everywhere in the circuit, correct? It doesn't matter whether it's before the component or after the component, the current is the same. Are you with me? So when you put the fuse in the neutral wire, if the fuse blows, there will be no current flow. So it doesn't matter whether you put it in the live wire or neutral wire. So what I'm trying to tell you is, you cannot explain this in terms of current. Because if you explain in terms of current, it doesn't matter where you put the fuse. So we cannot explain this in terms of current. So what Geraldine says is correct. It must explain in terms of voltage. You cannot explain in terms of current. So when the current is too high, now the first part you need to explain in terms of current. The fuse blows when the current is too high. After the fuse blows, then you explain in terms of voltage. After the fuse has blown, what happens? Everything after the fuse will be at 0 volts. Everything after the fuse will be at 0 volts. Whereas if you have the fuse in the neutral wire and it blows, right? Okay, the appliance will remain at high voltage. Okay, sorry, the live wire, let's say, is 240 volts, right? The live wire will remain at 240 volts. The appliance will remain at 240 volts. In fact, everything will be at 240 volts up to the point where the fuse is. So in other words, if you explain this in terms of voltage, you have to make sure that the fuse is as early as possible in the circuit in the live wire. All right? That means after the live wire, when the fuse blows, everything will be disconnected from the high voltage. It will be at 0 volts. But if you put it in the neutral wire, right, the appliance will remain at high voltage even when the fuse has blown. Do you understand? Even when the fuse blows, there's no more current flow, but the appliance remain at high voltage if you place the fuse in the neutral wire. Are you listening? Huh? Any question? Do you understand what I'm trying to say? Okay? You cannot explain in terms of current, because if you explain in terms of current, it really doesn't matter where you put the fuse. Anywhere you put the fuse, it blows already, there's no current. You must explain in terms of potential or voltage. Okay? Because before, when the fuse blows, everything before that remains at high potential. Alright? So if you place it in the wrong place, everything remains at high potential. So the way to answer the question, okay, so you look at the way we phrase it here. First part of the answer is, if I connect to the wrong place, neutral wire, what happens? Even when the fuse blows, the voltage of the appliance remains high. Okay? Then if you put it in the correct place, live wire, when the fuse blows, the voltage will now be 0, or you can say the appliance is disconnected from high voltage and the user is safe. All right? Why? Jonathan, tuition. Okay. Okay. Are you all done? Anyone have any questions? If you can wait for 5 minutes, I explain the function of earth wire. It's important. Okay? I explain the function of earth wire first. Okay, earth wire, right? Okay, earth wire works together with the fuse. Earth wire works together with the fuse. So the earth wire is connected to the earth as what the word says, right? Suggests. So if you look at this diagram over here, okay, you have the live pin, which is at 240 volts. You have the earth and neutral are at 0 volts. Okay? The earth wire is always connected to the metal casing. The earth wire is always connected to the metal casing. So what happens is, if the live wire comes loose, right, and is frayed, and it touches the metal casing, all right, the metal casing will now be live. Okay? Will now be live. Live meaning 240 volts. Okay? Okay? When the live wire touches the metal casing is now live, it's dangerous. That means if you touch the metal casing, you get electric shock. Alright? But the earth wire, which is connected to the metal casing, provides a path which is of 0 or close to 0 ohms. So it's a low resistance path. The current will flow through the earth wire instead of through the person touching the metal casing. You understand what I'm saying? Right? So the current will now flow through the earth wire instead of the man touching the metal casing. So that is providing a low resistance path for the current to flow. But the game is not game over yet. It's not game over yet. Why? Because the current is flowing directly from live to metal casing to earth wire without passing through the 30 ohms, the heater, the appliance at all. There's no resistance. There's no resistance. It's going directly from live to metal casing to earth. What do you call this? No resistance. Short circuit, very good. So when there's a short circuit, what will happen? The person doesn't get electric shock, but he may die of a fire. Okay? So even though he doesn't get electric shock, but then the next thing will happen is a fire because of the short circuit. Right? So the story is not over yet. What then must we do? Yeah, that's where the fuse comes in, right? So when the current flowing from the live to the metal casing to the earth is very high, what happens to the fuse? The fuse will blow. Okay, so when the fuse blows, then everything after the fuse will be cut off from high voltage. And then the user is safe. Understand? So the earth wire works together with the fuse. Alright, so in this, okay, y'all can carry on. Right, so the text over here, you just highlight the keywords. Always remember that earth wire is connected to metal casing. Okay, in the event of electrical fault, please don't say in the event of live short circuit. Short circuit is not the same as electrical fault. Electrical fault is when a live wire touch metal casing. Okay, so live wire touch metal casing cause it to be live. All right, the earth wire conducts the current into the ground. Large current will flow, and when large current flow, the fuse will blow. It will disconnect the appliance from high voltage. Okay? Any question? Okay, the switch is exactly the same issue as the appliance. Okay? Same issue as the appliance. So if I were to draw the same thing again, this is your appliance, right? And this is your live wire, this is the neutral wire. Your fuse is here, right? So where do we draw the switch? Okay, usually the switch would have to be over here, just after the fuse. Hey, let me finish. Come on, 3 more minutes. Okay, let me finish. So the switch is just after the fuse. Okay? If you put it in the wrong place, what will happen? Won't explode lah. Not so dramatic one. It will just subtly continue working until one day something goes wrong, then you die a horrible death. Okay? Right? So, if you connect it wrongly, right, actually it will work just fine. Okay? Until one day, okay, when there is an electrical fault. Okay, I want to delete the fuse because the fuse will give me a problem in terms of explaining. So let's not talk about fuse here. Let's just talk about switch only. Okay? So if the switch is in the neutral wire, right? What will happen? When the switch is open, there's no current flow, no problem, right? You don't sense anything, no problem. I open the switch, it's not working. I close the switch, current flows, it's working, no problem. But until one day, when you open the switch and then you plug out the appliance to repair it, okay, the switch is off, right? The switch is off, but the appliance is still at high voltage. You touch the live wire, you get electric shock. You understand what I'm saying? That means there's no current flow, no? But the live wire is at high voltage. Okay, so it's the same issue as the fuse. Same issue. So if you understand the fuse, you understand this with no problem. That means that everything up to the switch will remain at high voltage. Everything up to the switch will remain at high voltage. The appliance will be at high voltage, the live wire will be at high voltage. Understand? It's still dangerous, even if the switch is open. Okay? But if I put a switch in the live wire, when the switch is open, the appliance and the live wire will all be at 0 volts. Okay, so that's why the switch must be also in the live wire. Is that clear? All right. So although just now I told you about the live and neutral, if you swap, although the fuse is still in the live wire, but your switch of your appliance, is now in the wrong wire. Okay. So no matter what, you shouldn't try play punk and switch the wires. Okay. This question came out for O-level before. Okay? Came out for O-level before. So just take note of that.